I have talked about models of computation in the previous week, so I'm just going to go over this part really fast. So if you recall, the model of computation that we use in theory when it comes to computational geometry is this model that is known as realRAM. It is a random access machine that is equipped with integer registers as well as real registers. So the real registers can store any real number up to infinite precision. And you can perform operations, normal arithmetic operations, including the kth square root of a real number in constant time, and you can store the result in a real register. And the reason I covered the reasons why we need this in particular, otherwise this problem, we don't have currently a polynomial time solution for a simple problem, whether the red path or the blue path is shorter. So that's a theoretical model, and in practice this is justified by saying that floating point numbers provide a very good approximation for a real RAM. Even though we don't have a real RAM in practice, we can just substitute floating point registers or floating points instead of these real registers. Okay, but this causes some issues because obviously you cannot represent real numbers exactly with floating point, right? So you have a limited number of precision with a floating point, or fixed precision, in fact. This causes a lot of problems. In particular, floating point operations are imprecise. Hopefully next week I can do some in-class exercises with you guys too, so that you understand some of the issues when it comes to floating point operations. And many of the issues could be non-obvious. So if you've been thinking about floating point operations as precise or exact, you really need to change your perspective here to have a good chance of coding something reasonable in computational geometry. In particular, the imprecision can cause lots of weird stuff to happen. So for example, you have a triangle, this red triangle, and you have a line, right? So this line goes through this triangle. So obviously if it intersects one edge of the triangle, it must intersect one of the two other edges. One of the common things to solve in computational geometry is that you have a line like this, and you want to know where does it intersect this triangle. One way to do this is to say whether it intersects. Let's say you have this intersection point, right? So you know that the line intersects this edge of the triangle. You want to know which one of these other edges are intersected. So what you can do is that you can test whether this line segment intersects a line or this line segment intersects a line. We have covered this using geometric predicates, if you recall. So our geometric predicates can answer which one of these two line segments intersects the line. And the answer could be none of them because of the floating point issues. Why the answer could be none of them? Well, for example, if these line segments are given by the points here, and then you put them in a formula to get the equation of the line that goes through those points, that conversion is inherently imprecise. And it is possible that due to this imprecision, you get that the answer is no. So let me show you a more convincing example. So imagine the triangle looks like this, and the line that you want to know intersect goes essentially very close to this intersection point. Then let's say this guy is not intersecting, so this line segment is above. This line segment is below, but this line segment is intersecting, but it's barely slightly intersecting. It is possible that due to floating point errors, the triangle actually looks like this, right? So due to floating point errors, you can have this shape where the triangle is not essentially closed because I have errors in my computation. So then if you have an algorithm that depends on this fact that if a line intersects one edge of the triangle, it must intersect the other two edges, then you have a problem with a flawed logic, in a sense that in practice this logic is flawed. Because even though from a geometric point of view we know that if a line intersects one edge of a triangle, it must intersect one of the other two edges, in practice none of it could be true. So therefore whatever you code must be robust enough to withstand these floating point issues. In particular, such floating point issues can cause infinite loops in your algorithm, which are extremely difficult to debug. And different operations can suffer differently from floating point issues. Again, we're going to talk about this probably during the class, But basically, some operations are more complicated than some other operations. So for example, finding the intersection point of two lines is complicated. So if you want to know whether the intersection point of two lines is above or below a line, then you're doing lots of floating point issues. In particular, if you multiply and add different floating point numbers to each other, then you're essentially, every operation increases your error. We're going to look at floating point, again, as I said, more in the class later. The solution, there's a main solution here. There are lots of libraries that offer floating point numbers with variable precision. So for example, there is this notion that you could have a floating point with a technically infinite or unlimited amount of precision in it. And then the library will dynamically adapt. If you run a calculation and the library realizes that there is error in it and then the result is not precise, it would calculate the floating point numbers to a higher degree of precision. Obviously, the problem is that those libraries make your code slower. Something else I want to talk about here, this might not necessarily help with every kind of floating point error, but it can help in some cases. And since it's a useful concept, I'm going to look at it next. And here what I want to talk about is this notion of symbolic programming. Let me show an example that shows what I mean by this. Imagine you have a code like this, that you want to find the maximum of a bunch of numbers in an array. You initialize the max to minus infinity, and then you run a for loop. And then you compare your ith number to the max. If it's larger, then you update max, right? So that computes the max. How do we implement this code in practice? Because obviously I cannot assign minus infinity to the max. And let's say I don't want to change this code, because one way to change it is to say that to initialize max to say A1, and then I don't have this problem. Then the max is initialized. So let's say I don't want to change this code at all. If you think about this, the number of potential solutions, one of them is that, well, you can substitute minus infinity with the smallest number that you could represent. That's one solution. The solution is that you can add a Boolean variable, because what we're doing here is basically saying that, okay, max is not initialized. The first time we do the assignment, or the first time we do the comparison, has to be assigned or initialized. So we can do it using a comparison. In other words, over here, first you do an if statement check whether max is initialized or not. If it's not initialized, then you initialize it to A1. Otherwise, just you do the comparison. But what I'm interested in is the idea number 3. And the idea number 3 is that just make minus infinity and plus infinity valid choices. Just treat them as potential values for the variable max. Obviously, we cannot do it with the basic variable type or basic data types, because the basic data type int or long or whatever doesn't have minus infinity or plus infinity in it. So to accommodate plus and minus infinity as valid choices for a variable, we could make max an object or a complex data type, which allows assignments of numerical values to max as well as plus and minus symbolic values. Why is this useful? It is useful because if you go to higher dimensions, then we could have essentially the concept of a point at an infinity. A point at infinity can be defined along any line. So this is a line in 2 dimensions, and I can have a point at infinity over here, and as well as a point at infinity over there. And then you could define, some geometric object using these points at infinity. For example, you could define an array to be a line segment that connects a point, and let's say a normal point, to a point at infinity. So which point at infinity is this one? It's this point at infinity, right? So the point at infinity that is along this line, essentially any line parallel to this blue line also is good enough. Okay. In other words, in this notion, we consider all of these points to be the same point at infinity. Okay. We're going to visit this concept later on when we talk about when we talk about projective plane. But this is a kind of a powerful notion and the basic idea is that using these symbolic representations, you could actually augment your predicates to be able to handle these symbolic points. So for example, if I define a point at infinity along this line, how do I know whether this point has infinity below or above the red line? So let's say I want to do orientation test. with this symbolic point. How do I do this? Just pause the video and think about it for a second. And this is a hint. So in this case, the point at infinity is above. In this case, the point at infinity is below. If you thought about this, you realize that you can do this by just comparing the slopes. Okay. So by comparing the slopes of the red and blue lines, I could decide whether this point as an infinity is below or above the red line. Okay. So here the idea is that we can treat points, lines, etc. as complex objects. And we could have predicates that can take care of these complex objects. We could have symbolic values for these objects, or let's say values that are not traditionally represented by numerical values for them. This could make coding the rest of the program less complicated, because we can have now the representation for rays, or parallel lines and things like that, which could be difficult to achieve using numerical values for lines because of the floating point issues. Okay. So what do I mean by that? So now what I mean is that if you have two parallel lines, you could have two lines parallel because they pass through the same point at infinity. Okay, so that's one way to define parallel lines, which is a symbolic way of capturing it in your code rather than by having their slope to set to exact values or equal values. Okay. And that's basically all I want to talk about in